What is up, car and craft fans? We're back today and we're going to do something really interesting, which is look at how we build custom lighting for your car. Now, for me, I'm doing this at the moment because in my 350Z, in the ducktail spoiler, I wanted to integrate a brake light that also did some other stuff. So what I needed was a way of building a custom brake light into there that works off the internal circuitry of the car, but also allow me to program it in different ways. So what we're going to do in this video is I'm going to show you how to build a circuit for an Arduino that can interact with the existing circuits in your car and control custom lighting. Now, you might use it for brake lights, for reversing lights, for all that kind of stuff. Mine's got a few little custom things which we'll touch on in this video, but this will be part 1 of 3 about this setup. The first one here, we're going to go into everything you need in order to get it to interact properly with the car, how to build the basic circuits, and an introduction to the Arduino programming language. And I'm going to show you that it's actually not all that scary to start to program that stuff together. So if you've just ever thought to yourself, I want to make some custom headlights, custom tail lights, custom any kinds of lights in your car, but you don't know how to get it to all interact with each other, this is the one for you. I am approaching this from a perspective of if you've never ever done this before, you don't know how to use an Arduino at all, you don't know how to use a programming and prototyping board at all, hopefully all of this you'll be able to follow and get to the point we get to at the end. So we're going to dive into it, and I'll start by showing you all the pieces that we're going to use. First up, let's start with this weird looking thing. What this is a pseudo matrix. So what a matrix is in lighting terms is a grid of lights. Now, I didn't want to use a pre-made matrix of lights. Big reason is custom sizing, and it can be difficult to get the sizes right. Also, when you're using a matrix grid, the addressable LEDs, the individually addressable LEDs, it's not quite as easy to play with things like brightness, which is something we're going to need for this light. So this is a 3D printed case, which I've crudely taped together for now. And it's a single long stream of LEDs that go back and forward all the way up the board. It enters from one side here, and at each one of the ends, the wires have been soldered on to allow the circuit to continue to go up and down. So yeah, this is just basically a long single strand that goes back and forth. It means that these are all individually addressable. I can control the brightnesses, plus, as you can see by the rubberized topping, this is an IP64, I believe, is the name, IP64, IP65 standard, which allows them to be waterproof. When they're going in the back of a car inside a ducktail spoiler, that's quite an important thing. Also, you'll see the ends are absolutely coated in hot glue. It just allows me to make sure nothing moves. Plus, again, it helps with the water tightening at the ends where I've had to cut them in order to solder them end to end. So really, this is just a big light. If you're going to be doing this, you might do it initially with just a NeoPixel strip, which is a single long line, and then you shape it afterwards. So that's what we're looking at here, and it has 3 signals, or 3 wires. Red one, which is 5-volt power, the white-ish one, which is the ground, and the middle green one, which is data. Then we have this is a prototyping board. What this allows you to do is connect all of your circuits up in a temporary fashion before you move it onto your final breadboard. How it works is the negatives here all are connected across the entire row. So anything that you put in the negative here will be accessible across the entire row. Same with the positive. So if we put a ground and a power input here, it's available across the entire row. Then all of the columns are interconnected but split in half. So if we take, for example, column 30 here, anything that we put in column 30A, the top one, is also available in B, C, D, and E. So they're all interconnected. which means, you'll be able to connect up circuits really easily. This will all start to make more sense as we start to build a circuit. The heart of the whole operation is an Arduino board. In this case, we're using Arduino Nano. It's one of the official Nano boards. Super easy, nice small prototyping board, and I always buy pre-soldered. Soldering all these things is a nightmare, so just buying them pre-pinned is going to make your life a lot easier. So this is the heart of the operation. This is the actual little computer. Doesn't need to be overly powerful for what we're going to do, and so this one will do the job just great. We've got these little buttons because of the way that we're going to be doing an iterative design process. So when you're building circuits and when you're doing any kind of programming, you don't try and write the whole thing in one go and press go, because there's a good chance something's going to be broken and it makes it really difficult to debug it. What we're going to do is build things slowly, and we're going to test it as we go. So we're going to use buttons that we actually don't use in the final application, because these are going to simulate certain things that we're creating. Then we've got the two things that are a little bit more unusual. First one here is, this is because we're going to be putting it into a car. This is a 12 volt to 5 volt voltage regulator. So what it allows us to do is take a V in and a V out. So what we can do is put a 12 volt circuit, so your battery circuit from your car, into here, and it will give us exactly 5 volts out. Then we have perhaps my favorite of the boards. This is an optocoupler, and this in particular is a 12 volt, as we can see on the bottom here, marked 12 volt to 5 volt optocoupler. I'll explain this in detail later, but really what it allows us to do is put in up to 4 circuits in pairs here in 12 volts and have them come out as 5 volt circuits. So we'll be able to put our brake line in here and our reversing line in here, and then have them come out at the other side in 5 volt circuits. We'll get to that towards the end. Then we've got a load of these jumper wires, which we're going to need, and some capacitors. Also, we're going to need a computer. Mine is connected to this, to a USB port, and you're going to need the Arduino EXE program. This is it. When you start a new application, this is what we start with. I'm going to break down all of this for you as we go through. Right, so first things first, let's stick our Arduino onto our prototyping board. I'm going to put it right at the end here, and just to make life easy, I'm making sure that the USB port is facing outwards, because my USB wire is on this side and it's just going to make it easier to plug in. If I start by plugging in this, it's going to light up. It shows us that our signal is going. And then I need to go to my application, and I'm going to do a couple of things. I'm going to open up the tools, and you need to look in your boards management here to ensure that your board is the right one based on what you have. So I'm using an Arduino Uno here. This is set up for an Arduino, but I'm actually running a Nano. So I'm going to change that to Arduino Nano. Then we can check the port. So you can see mine as pre-selected port COM3. That's a USB port. It means it should be ready, should be all good to go. And yeah, processor's fine there. And the programmer, the one that you use here, depends on your board. So just make sure that you look up which programmer it would be using for your board. For a Arduino Nano, you want this one, the AV-RISP Mark II. For example, if you're using, say, a Trinket, you might use USB Tiny ISP. So just, you just need to figure that one out. A good way to know if we're all good is, what we're going to do is upload the sketch. You'll see it compile, and then uploading, and then done uploading. Great. So that means it's successfully connected to our board and uploaded this little blank package that does absolutely nothing. Step 1, complete. We are now talking to our Arduino. Dead simple. Now I am about to start writing code, which means I have to go into geek mode. Otherwise, I'm going to get a headache. Okay, so what is the simplest thing that we can do? The simplest thing is going to be get power to our lights and turn them on a basic color. So that's what we're going to do first. We're going to set up what I'm going to call DRL mode. So daylight running light, which is what a DRL is. So we're going to get power from the Arduino for now and power up the lights. That's going to be step one. So let's start by building the circuit. Whenever you're building a circuit, make sure you turn it off. It is going to just stop any kind of like irregularities with the voltage. So on our prototyping board, there are a variety of different pins down the side, and they all do different things. So you've got along this side D2 through to D12. These are our digital pins. They control inputs and outputs. Then on the other side, we have a bunch of A pins, so A0 through to A7. Those are analog data pins. We're actually not going to be using any of those. And also, if I just flip it over, you'll see we've got 5V, ground, and V in. These ones are going to be used. So 5V is the 5 volt output that this nano will put power out. V in is our voltage in, which we are going to need to use at some point, but that's later in the circuit, and ground is ground. So we're going to use this initially to power everything. Like I say, it is an iterative process, so that's not going to be the way forever. So we're just going to grab a few different small ones of these. And we're going to start by connecting the ground, because we always take best practice and do ground first. So the ground is here, and I want to put the ground into this track across the top. So I can use any of the column and any of the row. So we can see there, I've gone from one of the column next to the ground pin, and I've ended up in this row, which means this entire row now has ground to the Arduino. Then, similarly, I want to do power, which I'm going to do in black, from the 5 volt to the power. So starting the power there, into the 5 volt, which means now we have 5 volt power across this entire top row. So anything that I plug in to the top, into these top two, into the power and the ground, will be powered from the Arduino. So that's what we'll do to start with. We're going to take our lighting setup, and we're going to plug in power into power at the end, ground into ground. And then we're left with the data. Where does the data go? Well, we're just going to pop the data into a hole in one of the rows at this end. There. Now at the moment, if we turn this on, nothing is going to happen. These have power, but they don't just turn on. That's not how these programmable, addressable LEDs work. You're going to need to give them a signal to say, what do we do when the power powers on? In order to do that, we're going to take one of our digital outputs and connect it to this data line. So we need a nice long one of these, connected into the same column here, and then into one of our data lines over this side. We're going to go into D2 because we can reach it. D2. Great. Believe it or not, if you were doing the simplest version of this application, that would work. Now, it's not ideal to be powering this from the Arduino, and it's not what we're going to be doing by the time we get to the end of the application. But this would work if we programmed it. Let's build the program that's required to make this thing work. Now, when we're building an Arduino package, you're given, like I said, this to start with: void setup and void loop. Void basically means it's just telling the system that it's a type, but it's not an integer, it's not a number, it's not a single 10 byte, it's not a string of text, it's a nothing. It's a void. It's just a way of holding information. So setup runs once. When we start the Arduino up, setup runs. After setup has run, loop continues forever. Here's a good way of showing that this is working. You're going to want to understand what serial connections are. So if we go to Tools and Serial Monitor, the board isn't available. So let me just plug the board in to start with. Tools, Serial Monitor, there we go. So we'll end up with this thing. This is a really good way of just testing and running what is happening. And in order to use the serial board, you need to tell it to start, and it has a predefined way of doing it. And it's using the code serial.begin and giving it a baud rate. It's basically a speed that the signals run at. For this, you're generally going to use 9,600. So that will tell this thing to start, and it's basically telling the serial to monitor what's going on. Then there's another bit of pre-made text that we used, which is this, while not serial. This is an instantiator that you need for a lot of different prototyping boards. We don't need to go into why you need it. It's not important from this level. Just put it in. And then we're going to do the thing that you're going to use a lot, which is serial print ln, which is short for line. So print a line saying whatever you want to say in here. So we're going to say serial started. So the difference between print and print ln, print will print it, but if you run lots of print commands, they'll just go one after each other. Whereas if you do print ln, it'll do it and then it'll start a new line. So it makes things a bit more readable. So what we'll do is upload that. When you click upload for the first time, it is going to ask you just to save it. So we'll save it as light setup. So you see it's compiling, built, and there you go, serial started. So what's happened is I've clicked upload, it's gone to the program's gone to the Arduino's restarted, and it's run that program, which has ended up in the serial started. Then, just to show you how the loop works, if we would go serial.println, do a loop, and we upload that, you'll see that again, it will restart, it'll give us a start command, and then it will loop forever. And that will just keep going forever. That's what loop does. So loop is constantly listening for changes of state, changes of environment. So we've got our board set up, and now we need to start connecting up the lights. So the lights are going to require something, and it's the code, the package that manages NeoPixels. I already have it downloaded. So if I go to my include library, I have the, there you go, Adafruit NeoPixel, which will include this Adafruit NeoPixel package. It is available if you go just into the package management. It is there, which is in include library and then manage libraries. You can go and find it, but I have used it a bunch, so it's there. And what that does is give me access to all the code that NeoPixels require. So I need to start setting everything up. So before we go into the code that starts working things, we're going to start defining some things that we'll use often. And we do that with the define keyword. So it's hashtag define. Then we can write the thing that we're defining. So the only thing we've put in at the moment is the pin that you remember we put into pin slot 2. So the pin for the pixel, so for the lights, is number 2. And then if we use this // we can just write ourselves notes as we go, which remind us what we're doing. So that's the pin for NeoPixel strip. So this here might be pin definitions. Then we're going to want to have another few things that just tell the lights what we're doing. So we're going to have, let's go call this LED attributes. And the first one, something that's never going to change, is the number of pixels. So our number of pixels happens to be 186. So that's 31 per row times 6. So I've got 186 pixels. Also, these pixels can go from a brightness of 0 through to a brightness of full brightness of 255. So I know that later on down the line, I'm going to want to add a brake light. So my brake light will be full brightness. So my non-brake light, my daylight running light, can't be full brightness. It needs to be muted. So we need to pick a lower number. So what I'm going to do is define two things. The max brightness, which will run at 200. And also we'll define the normal brightness as a much lower value. Let's put it down to 10. These lights are surprisingly bright, so it doesn't have to be very high. When you're doing these definitions, you're trying to write things that are never going to change, but also that you might use a lot. So from now on, we can use this word, normal brightness, instead of 10. So if I want to change it lots of times in the code, I just change it once in the settings at the top, not all the way as we're going through. It's called dry programming. Don't repeat yourself. Then what we need to do is create an object that allows us to actually have the information for the pixels and where we send that off. Again, it's done in a predefined way, and it comes with the instructions for NeoPixels. So if you were to view the documentation that comes with NeoPixel strips, you'll see this bit of code. So it's Adafruit, who are the company that make NeoPixels, NeoPixel, then the name of what we want to call our NeoPixel strip. We're just going to use the word NeoPixel, and then a few variables. So what it wants is the number of pixels first, then the pin number that it runs on, so how many pixels we've got, what pin it's coming on, and then a predefined, bit of code that's just saying what the pixel values are. This is just one thing that you'll pull straight from the documentation. Not a specific bit that you need to understand in any great detail, but what you need to know is this thing, NeoPixel, is what we will be using to refer to the strip. So whenever we want to do something to the lights, we'll call NeoPixel. So that is, in essence, its setup. So then when the setup runs, if we were to send information to the NeoPixel strip, we can get it to start doing things. So the serial is all started and begun. That's listening. We need to start up the NeoPixel, which we can do with neopixel.begin. And now the NeoPixel will start up, but as of yet, it doesn't have any information about what it needs to start up to. All it knows is it needs to begin. So what we're going to do is create a very simple loop, in loop. So it's constantly listening for this thing that is going to send the information of what brightness is and what colors to send to the lights. So we need to create a loop. So we're going to create a for loop. And to do that, we do for and then start a new integer. So this is the thing that holds a number in it. We're going to call it LED number. So from LED number starting at 0 all the way through until LED number is less than number of pixels, which we defined here, number of pixels, LED number plus plus, which means increment by 1. So it's going to go, this loop is going to run from 0 through to 186. Well, actually 185 because it's less than, but our first pixel is pixel 0, so the number is 1 less. And what we're going to do for each one of those is neopixel, which is the object that we defined here, dot set pixel color. It's Americanized spelling. Then LED number, which we're taking out of this loop. So we're taking LED number. So it's saying set the first one. And to start with, let's just do red. So in an RGB format, red, green, blue, red would be a value, let's say 100, then no green, no blue. That is just RGB, so mid brightness red. And I'm going to get rid of this do a loop because it's annoying. So what this is do is go in and it says, okay, set all of these values for this strip. Then what we're going to do when it's stored all of those values is we need to do neopixel.show, and then that will set all of those new values that we've set and it sends them to the strip and it should work. So if we just click the plus, it'll verify, and it says that I've got an issue here because I've missed something. It's that. So then now that I've got this, I can just click upload. We'll see the serial restart. We upload. It flashes to show that the new command's there, and there we go. That is mid brightness red. We have successfully turned on all of the LEDs. Step 1 complete. Now, if we just wanted to achieve that, we'd just go out and buy a strip or a set of pre-programmed red lights that just hook up to the brake light in your car and come on. That's not enough. So we need to start playing around with these values and being able to control it a bit. So in the end, we're going to do that through the car inputs. But for right now, we're going to do it with buttons. And that's what these little buttons come into play. So remember when we're working on the circuit, take these off. So I'm going to put one here, and these things just slot in the exact same way as the Arduino did, and we can put them just next to each other here. So we're going to look at two different kinds of inputs. We're going to do a brake light and a reversing light. Pretty simple. When wiring switches to an Arduino, there are two ways of doing it. One, with resistors and everything in place, or you can use an internal resistor, which is built into the pins, which will make life a little bit easier. That's the way we're going to do it. Just means the wiring is a little bit different as well. So these two buttons are both going to need a negative on one of their arms. So the arms are kind of at each corner. So we're going to take the top left corner one here and connect it to the negative track. And if you remember, that whole track across the top has a ground in it already. So we'll do that on both of these. Then we need to connect the opposite one on the top corner. So the top two here are linked and the bottom two are linked. So we need to take the top ones and connect them to the inputs on this side of the board, the digital inputs. So we'll take two of these, start with one on the left here. So we'll go from here. I'm going to go into, let's go into the two at the very end here, 11 and 12. 11 and 12. Is that the right one? No, that's the right one. So those buttons are now wired into our circuit. The circuit comes out from here into the ground goes into the button, and then when the buttons are pressed, they complete the circuit. But we need to program them in. So let's go back to our button definitions here, and we're going to define the pin for the brakes as either 11 or 12. Doesn't really matter, but we'll go for 11. So that's pin for brakes. And we're also going to define pin reverse as 12. One thing we could do with adding at this point is telling the Arduino whether our pins that we're connecting up are inputs or outputs and what type they are. So we do that with the pin mode command. So we're going to start with our pin pixel, which we're just using, and that's an output. So that means data is only ever going to go out of it. Then we've got the pin mode for pin break that we've just set up. And pin break is an input, but it's a special kind of input because there's no resistor in there that's monitoring the flow of the voltage. We need to have that done through the internal resistor. So that's a pull-up, which is called a pull-up resistor. This is just basically telling it that it activate that internal resistor. And then we're going to do exactly the same for pin reverse. So pin reverse is an input pull-up. The only thing to watch out for with using pull-up and the internal resistors is it flips whether or not a signal is considered high and low when monitoring for a button press state. So usually if you had an external resistor, the circuit is low, and when you press the button, it goes high, high, high when you press the button. In this case, it'll flip that, so it's high all the time, and then pressing it will make it low, which I'll show you now. So in our loop, we're going to listen for those state changes with those button presses. And we do that by telling it we're going to create a byte. A byte is a single on or off. It's a 1 digit. And that is we're going to set the state of the brake. And the state of the brake is equal to the digital read of the pin related to the brake. So what this line simply does is go, as this loop is happening all the time, it's going loop, 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 loop. And that digital read is now listening to that pin number, the brake pin, which is pin 11, and going, are you high or low? Are you high or low? Are you high or low? And depending on whether it's high or low, depends on what brake state is set to. So that means we can use brake state later on to create things that change. So we also want the state of reverse. Ooh. So that is digital read pin reverse. So we can just check these, verify the code's all working so far, and it will give us warnings that we've created these, but we're not using them. That's fine, we're going to use them now. So at this point, it's worth looking at, like, what's the safety priority from this, from a car perspective? And the safety priority is the first most important thing is the brake light. You never want to have anything overruling the brake light. So the brake light comes first. So we're going to say if the state brake is equal, 2 equals, otherwise it'll set it, is equal to low. So like I said, because we've used a input, which is a pull-up type using the internal resistor, we're listening for low. If we'd use an external resistor and a non-pull-up, so just an input, we'd have state brake equals high. So if the brake state is low, we're going to set brake. And that's just a new function I'm just creating there, which we'll create in a moment. Else, if the state of reverse is equal to low, then set reverse. Again, another function that doesn't exist, we're about to create it. Else, so if those two things are both not happening, set DRL, daylight running light. So now we can do three different things: set the brake, set reverse, set daylight running light. But at the moment, all this code here just runs all the time. So we're going to want to get rid of this, and we're going to create three functions that do different things. It just helps separate the code out, makes things a little bit more readable. Like I said at the very start, we have a void type. It's just basically creating a function. So void, and we've got set brake, then we've got void set reverse, and finally void set daylight running light. These are our three functions. And so we've got the code already for the daylight running light. We've just defined it. So we're just going to copy that into here. Then just for simplicity, we're going to duplicate it 3 times. And instead of using the set values here, so at the moment we've got 100, 0, 0. So this is red, green, blue. So half red, green, blue. This is where our attributes that we set at the top, brightnesses and normal brightnesses, come into play. So our max brightness is 200. So when we're going to set the brake light, instead of just setting it to 100, we'll set it to max brightness. What that means, if I want to change the brightness, I just do it here at the top. Similarly, I can take normal brightness. So normal brightness can replace this 100 for daylight running light. And for the reverse, I want to use normal brightness, but I want it to be white. So all three, that's all when all three have got the same value. So normal brightness for red, for green, for blue. So now when set reverse happens, it should light up white. When brake light happens, it should be a brighter version of red. Otherwise, when daylight running light happens, it's just a normal muted red. So that successfully compiles. We'll plug this in. As you can see, it's still running our old code until we upload it. It is uploading and done uploading. There you can see it got less bright straight away. It got less bright because our brightness now is 10, whereas it was 100 before. So now pressing these two buttons does stuff. You see, so this left one is our brake, and when we're pressing it down, the set brake command is running, brake light, and then when we press the other one, reverse light. So it goes white. Brake, reverse. But also, brake can take priority over reverse. So if I hold reverse down, as if we're reversing, and then we tap the brake, it still overwrites it because it has the priority. That could be it. We could finish there. We could say, okay, we've got our brake light and our reverse light. So long as we can change these inputs to use the optocoupler and take signal from the car, and we power everything from 12 volts to 5 volts, hypothetically this all works. There's a problem though that might cause us issues down the line, and that's the blocking of the serial connection due to the way NeoPixels work and the way the loop currently works. Let me demonstrate what the problem is. So if I do a serial.println here, and we do braking, braking, and then I do one here, reversing, and I do another one here which says DRL. The problem is this. If we watch the serial output, the loop goes forever. Okay, so it's going DRL, 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 and does it really quickly. If I press brake, it goes to braking, and then if I press reverse, it goes to reversing. So the problem is, because it's looping and it's continually sending out things, you imagine it as the Arduino's telling the lights. This is how I like to describe it to people. It's going, be red, 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 be red. And it keeps going and it doesn't stop shouting be red until you suddenly come along and go, actually be white now. It's like, be white, be white, be white. And it keeps shouting all those things. Now for version 2 of this, which will be in the next video, where we use a Bluetooth module and integrate the want to be able to change the color of these lights through an application, this requires that serial connection. And if you keep having it, that it keeps shouting, be white, be white, be red, be red, be whatever, that signal that's coming in through the Bluetooth can't get through. Like you're telling it be purple and it's like be white, be blah, 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 and it muddles and creates junk data. So we need to basically get it to go, be red, and then stop. And then until it changes again, it doesn't need to keep shouting that information. It can just send it the once and then stop and listen. So we're going to create a very simple state manager. So what a state manager is going to do is going to do that. It's going to say, well, what are we currently doing? Do we need to change and keep updating? It's easy enough to do. It just requires, a couple of little loops in there to compare what we're doing with what we want to do. So in our definitions at the top here, after our LED attributes, we're going to create state management. Just state management. And in here, we're going to have various letters that denote states. So we're going to have D, which is DRL. Then we're going to have B, which is braking. And then R, which is reverse. That'll do for now. This will obviously expand as we build more things into the application. But right now, those are the only things that are required is DRL, braking, and reverse. So we're going to create a single character, a byte, and we're going to make the current state. So when the application starts, it's going to start up in D. It's going to start up in DRL mode. And also, we're going to tell it that the saved state is also D. One small thing to notice here is that I've used single quotation marks instead of double. You use double when you have a long string of text. You'll use single quotation marks for something like a byte here. So we're just going to have those two things start when the application starts. Then, okay, if we come down to our loop, what's going to change is this. So when the break state happens, we're going to say that the current state, which we defined at the top, so we defined current state and save state, but we're going to say current state when we're breaking is B. And then current state when we're reversing is R, and current state when we are doing anything else is D. And we're then not going to use these, at least not here. Then what we can do is say if the current state is not equal, which is what that means, to the saved state. So then we're saying, instead of this loop happening over and over, and then every time the loop happens, we go into one of these functions and we run that function every single time, we're only going to do it if the state has changed. So it's going loop, 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 and it's going, is D equal to D? Yes. Okay, do nothing. Is D equal to D? Yes, do nothing. Is D equal to B? No. Ooh, do something. So that's what it's going to do instead. So we're going to say if the current state is not equal to the save state, something we're going to change is instead of using an if-else statement, which could get a bit long if we have lots of different things that this program is going to use, we'll use a switch statement, which is basically saying, look at the value that we're going to switch on, see which thing it matches, then do that. So we're going to switch based on current state. And in the case that current state is B, so if it's break, then we're going to want to run this set break. And we're going to just put the word break in there. If you don't put break in, it'll just keep going down the list. By doing break, it's basically saying it's nothing to do with the brake lights. It's saying break this function. So break this switch. And then case of R, I'm going to set reverse. Again, break. And in the default, so if it hasn't matched anything else, then set DRL. Again, break. So the important thing to add now is that the current state and the save state are currently out of balance. So it's listening, is D equal to D? No. Yes. Is D equal to D? Yes. Is D equal to B? No. Okay, great, change. So now we're doing B, so the save state, B, has to become B. So outside of this switch statement, we're going to make saved state equal current state. Simple. So now when it's going, are these two things different? If it goes, yes, they're different, then it goes, great, well, we'll do that bit of code, but then we'll take the value of what we're now doing and save that to what we were doing, so then it can compare everything. So it just updates. The big thing you're going to see the difference of by doing this is in the serial monitor. So at the moment we can see DRL is still running over and over and over again, and it will continue to go probably for eternity. So I just verify that code, and then we upload it. And then if we watch the serial, we'll see serial started. When I press the button, braking is braking, let go, back to DRL, braking, DRL, reverse, DRL, reverse, brake, DRL, reverse, brake, reverse. You know, it runs once instead of running over and over and over again, because it's only saying only change or only keep sending out values when something changes. It's a step you don't really need to do, but like I say, later on, if you're going to do what I want to do, which is have things that can interact with this thing, so it's not just plug it in your car and away you go. I want to be able to get into there through a Bluetooth application and change things about. So I need to be able to communicate with the Arduino, so I can't have that serial port have noise on it. It needs to shut up, basically. That's what this does. So that's a really, really simple state manager. At this point, your programming is done. Now, this could be 10 different inputs, and they all do 10 different things. And you would just expand it out in exactly the same way. You'd come up here and you'd say you wanted to add in an indicator. You could define pin left indicator, whatever number it is. Go down and set it up, the pin, as an input, probably with a pull-up. Then we add another state in here. So if the indicator, the indicator might want to take priority over even the brake light. So we would, put it into this state block, which shows the prioritization, and then put the current state value into this state switcher. And that would be it. It would be added. So we could add as many of those things as we wanted. Also, if we want to start changing things like brightness and the normal brightness, we just change these values in here once. And so long as we've used them as defined variables all the way through here, everything will change in the same time. So from a programming perspective, that Arduino is now complete. There are a couple of things we're going to have to do in order to make it be able to work in a car, though, and that's predominantly the fact that these inputs need to be regulated 5 volts, which we don't have from... I'm going to apologize if you can hear snoring in the background. My dog is lying next to me, and she apparently is the most comfortable animal in the world and snoring away. But these inputs won't be buttons. These inputs need to come from the car, and they need to be 12 volt signals. So we need to know how to get them into these pins as 5 volt regulated inputs. Also, the pixel, the lights, really shouldn't be run from the 5 volts from the Arduino. You can do it, but you do open yourself up to like voltage regulation problems. Plus, with this many pixels, 186 is actually quite a few pixels. You do allow yourself problems. Really, you want some way of regulating the voltage, and that's what we're going to use these things for. So we basically just need to unplug this and switch around the way that it's wired a little bit. Now, I'm not currently in a car, quite clearly, and I have a car battery underneath my desk, but it is so incredibly dead. So we won't actually show you this functioning, but I'll show you what the wiring should look like, and we'll get to actually showing it you in part 3 of this video when we make all the connections and actually hook them up. So at the moment, this top track is powered by the 5 volts from the Arduino. I'm going to take that out. From now on, we want that to be powered by this little module, which is going to give us a steady 5 volts. So let's hook these up. So now that we've got this thing wired up, this is going to be the equivalent of, so we've got on this side the white and red, which is the 5 volt and the ground, and then 5 volt and the ground on the opposite side from the inputs. So on this side, we can simulate with these 2 wires, which actually aren't going to attach to anything. Let's do it the other way around. So blue for ground, red for live. These go to the car. So these are going to our switched ACC power. So when the car comes on and switches on, these 2 circuits connect. The Arduino can very happily take car's power directly. This one is already into the ground, so that's good. So that's where that's going to stay, is in the ground. These 2 can come out because all these switches are coming out. And then we can power this directly from the car battery. So we hook up the V in to the live line. Now, obviously we want to protect this against any potential voltage spikes. So that's when your capacitors come into play. Now I want one of these. This is a ceramic capacitor with the number 104 stamped onto it. The 104 that's stamped into this is really difficult to see. Indicates that this is a 100 nanofarad capacitor. It's basically just the capacitance that it works at. So if we put that there, I'm not worried about these. These are coming out. So let's remove all these buttons as well. So what we need to do is put this in that 12 volt circuit. So if we actually shift this back a couple here, so we can have the power come to one side of the capacitor, and then the other side goes to the negative. They're not in either direction, so it doesn't matter which side is which, as long as you have one goes to the power and one goes to the ground. It does a few things actually, but one of the big ones is just watching for voltage spikes and regulating the circuit voltage. So that's going to keep our 12 volts nice and consistent. How do I know to use a 100 nanofarad capacitor? You can use applications like this, Circuito.io, and you can build your very basic circuit and it'll tell you what capacitors to put in there. It's pretty useful. So this is a rundown of how my circuit will end up by the end of part 3, though it's slightly different. But this will tell you the capacitors to use, and we can see here the ceramic capacitor at 100 nanofarads, which connects to the positive and negative terminals directly into the breadboard. Then, as you can see here, we've got a bigger capacitor, which runs and connects to my circuit for the monitoring the 5 volts connection. We haven't set that up yet, we're about to do it. So, as we've said, in this top line, we've got 12 volts running across the top and 12 volts running across the bottom. And then that has a capacitor in it, which keeps it nice and level now. But that means this is now getting 12 volts, which we do not want because we'll kill them. So we want to now regulate everything down to 5 volts. So our module here is a 12 volt to 5 volt. So we're going to put the live in one side over the end and the negative, which means when everything switches on, we're going to get 12 volts into this side and it'll put 5 volts out the other side. So we're going to put 5 volts into this bottom track, there and there. Now this is in loop. We've got 12 volts on this top one, but 5 volts regulated on this bottom one. So now we can connect the lights up to a 5 volt circuit. So if we put the live in the live down here, and the ground, and then pop this back where it was, we now have the lights hooked up to the 5 volt regulated through the module, which is great. That's exactly what these need. Then we need to think about, first we need to just remove those, and then we need another capacitor that's going to watch this 5 volt circuit, and that capacitor needs to be a bit bigger. We're going to use one of these. This is a 1 microfarad capacitor. It's about 1,000, so this is 100 nanofarads, so this is 10 times the size. And if we pop this over here, let's bridge this over there to there. That's on both sides. On one side, we're going to go again to the negative of the core circuit, because everything in the end all grounds back to that same circuit. It doesn't matter if we ground on the left or the right side. But what's important is then this one on this side comes to the 5 volt circuit. There you go. So now we have this capacitor in place that is regulating the 12 volt circuit, the 5 volt circuit. So there is a nice steady 5 volt circuit and a nice steady 12 volt circuit. The 12 volt circuit actually is only doing anything for the Arduino. Everything else is powered by this 5 volt circuit. The last thing we need to use is an optocoupler, this cool little thing. So how this works is you have a signal input that comes in one side in pairs. So it takes a positive and a negative, as you can see here. Signal 1, circuit 1, positive, negative, circuit 2, positive, negative. So it takes a live and a ground, live and a ground, live and a ground for 4 different circuits. When one of those is on, so let's say you're driving along and this one is connected to your brake light. When you brake, it completes this circuit, switches on this light. It just shows you that it's working. Inside here, so there's 4 of these. Inside here is a tiny little UV bulb that switches on when that circuit's completed. On the other side is a sensor that senses UV light. So it goes, okay, this circuit's completed, turn on output 1. So we've got outputs 1, 2, 3, and 4, which link to these sides. What it allows us to do is have one 12 volt circuit change the state of a 5 volt circuit without them ever actually interacting and touching. It's just one of them has a light and the other one is looking for that light. So it's really good at doing it without any kind of like power disruptions. What this does need though is a ground and a live 5 volt regulated. So if we hook the wires up to that. So with this wired up for power, we have a 5 volt regulated circuit here, which we're going to connect to our 5 volt track. So we're going to take the power from the live, and we're going to take the negative ground from there as well. And there. And we're going to pretend that these two go off to various 12 volt circuits in the car. So this one here goes off to the ground and the live on your brake, and this goes onto your reversing light. So you can literally just tap into those lights. Then we need to hook up these two, so 1 and 2, which are 1 and 2. I'm going to hook up to 1 and 2. So we've got these signal wires for 1 and 2. So if we remember from our code, our break pin is 11. So that connects into 11. And our reverse pin is 12. So this connects into 12. And that is the completed circuit. Now I can't show it you running because I don't have a car battery here that is running, but you can take my word for it, and why would I lie to you? But yeah, that will run. So our 12-volt signal comes in here, which powers the Arduino, unfiltered, so just straight in 12 volts. It also powers this 5-volt regulator, which then powers the output switches here in our opto coupler. But also there are other 12-volt signals coming in directly from the car, whatever these might be. Obviously, if I plug it in now, it's not going to work because none of this is going to have power. It's just the Arduino is just going to power on. But if this was all hooked up to the 12-volt circuit, that would be it. It would work and it would run, and it would have voltage regulation through the capacitors, and everything should be hunky-dory. But the reason I can't show you working right now is there are further steps for this for me, for what I'm doing for the project for my car. So I have underglow in my car, and when I set it, it gives me an RGB value of what the color is using GlowKit's application. And what I want to be able to do is take that RGB value, put it into an app which I build myself on my phone, and then press a button and it communicate with this Arduino and set the brake light at the back to be the same color as my underglow. So when I'm at shows, if I'm parked up, I can leave the underglow on, but I can also leave the cool lit up because it's in the back of the car as a big 350Z sign in my ducktail. So I can light that up in the same color. So I need to be able to talk to this Arduino. So video number 2 is going to be taking this. This is a Bluetooth receiver. It is a low energy BLE-HM10 Bluetooth receiver, and have this talk to the Arduino and connect those signals, which is why we put that state manager in there. So it had the availability to talk to this thing through the serial connection, but also then build a mobile app which can talk to that and send and receive color codes from the phone to the Arduino, allowing us to change the color. So I do need to do all that first. Also, when you complete a circuit like this, you don't just install it in the car looking like that, because that would be crazy. What we do is build a proper housing for it. So we use things like these breadboards, which are the same as these circuit boards. They're not interconnected. We have to solder all those up. But as you can see, I've like pre-chopped this one, and this opto coupler actually has these building blocks in the corner, which are part of sets you can use for creating these things. But the holes in the corner of this weren't big enough. So they actually all come though as predefined sizes. So we can start taking these elements, soldering them onto these things, then building a container and having things like harnesses that go onto the end with switches and harness couplers that connect in and out of the car. That will be doing all that and setting this up and actually putting it in the car will be video 3. And video 2 will be doing all of the interaction and being able to talk to the Arduino and change things like the settings and the file and the colors and all that kind of stuff via a Bluetooth app. So we'll do that as the second video. Hopefully that's made you realize that you can actually, with very, very little programming, get something up and running for your car. So you could do that, and then you can start to play with this code. You might want to start doing flashing lights or animations. You're going to have to figure that stuff out yourself until we do a video on it at some point down the line, but I can't say when that's going to be. But hopefully that's made you see that the programming actually isn't too difficult, and hopefully I've explained it in a way that allow you to actually be able to understand what the code is doing rather than just saying, how write this code. I think it's important that you understand why it's doing what it's doing. And also that the circuitry isn't all that difficult. Capacitors are sometimes a little bit of a pain to understand, especially when you then start to get in resistors and circuits and all that kind of stuff. But we can mitigate a fair bit of like resistor use by using the pull-up resistors that are already in the Arduino, and it does make our life a fair bit easier. So if you are following this process and you got to here, you could go out now and throw all this into your car and it would work. But yeah, that's it. Geek mode ended. Time to go back to doing cool stuff. Not that that's not cool, it's just a different kind of cool. Obviously, if you do want to see the next stages of this build and using this and then integrating it properly into my ducktail and making this custom brake light spoiler thing that I'm concocting for my 350Z, make sure you hit the subscribe button, because, you know, that'll make you know when the next video's coming out. Oh, that's been a lot of talking in this one and a lot of technical stuff, so hopefully you managed to follow it along. But yeah, make sure you like and subscribe. Helps me a lot. Love you for it, and we will see you in the next video. Take it easy, people. Bye-bye.